1990 from this alma mater, that is VSSUT, then called UC Bulla, and has obtained his MTech degree from Birla Institute of Technology, Mesra, after which he joined in NIT Rourkela as a lecturer in Mechanical Engineering Department in the year 1993. Sir was awarded with his doctoral degree in 2005 from NIT Rourkela in the field of plasma spray coatings. Since then, he has been engaged in active research in coatings, composites, and material science for the last 20 years. Sir has 350 research publications, including about 120 publications in international journals of high repute, with more than 4,000 citations. Sir has presented about 225 research papers in various conferences and seminars that include 30 conferences abroad itself. Sir has guided a number of MTech and PhD scholars, out of which 12 have completed their PhD and 50 students have completed their MTech degree till date under his supervision. Sir has also authored 3 books, namely Novel Coating Materials, Composites for Microelectronic Applications, and Natural Fiber Composites, published by Lambert Academic Publishers, Germany. In 2004, he took part in the international workshop on advanced tribology at the National University of Singapore and received the Best Overseas Participant Award. In 2006, he was the recipient of the Best Oral Presentation Award at the 21st International Conference on Waste Management at Philadelphia, USA. He has received several awards and recognitions for his literary works and scientific research. They include the Literary Champion Award of Sambalpur University in the year 1990, Young Writers Award by Youth Hostels Association of India in 1994, MHRD Award as Non-Hindi Speaking Hindi Writers in the year 1997, SJ Memorial Award in 2006, and GM Memorial Best Research Paper Award by Institute of Engineers India in 2009. Due to his excellent teaching abilities, Sir has been bestowed with the first Best Teacher Award in NIT Rourkela in the year 2018. Apart from academics and research, Sir is also a certified teacher of Raj Yoga in the Prajapita Brahmakumari Ishwariya Vishwavidyalaya. He has an MSc degree in spirituality and an MBA in self and stress management from Annamalai University. He is a trainer and counselor in mind meditation and stress and self-management. Sir is an ardent traveler and has traveled around 16 countries on different occasions around the globe. Presently, Sir is serving as a professor in the Department of Mechanical Engineering in NIT Rourkela. Today, Sir is going to present on the topic Plasma Spray Coatings of Industrial Waste. Sir, please.
Can you hear me?
Yes, sir.
And can you see the slide?
Yes, sir, we can.
Acha, just confirm the change of slide. Is it happening?
Yes, sir.
Okay. Okay, good morning once again. And thank you, Devasmita, for my introduction. And today, as you have suggested, I will be speaking on plasma spray coatings, and more particularly development of plasma spray coatings using not conventional spray grade materials but using industrial wastes. And these plasma spray coatings are very close to my heart because I have been working in this area. I was working in this area for many years, and in the process we tried many industrial wastes to convert them from waste to wealth and for value added utilization of these materials into plasma spray coatings. So I will start this topic from a word called surface modification. As mechanical engineer, we know that whenever we have a component, like the design of component from the strength point of view is important, its modification, surface modification is also important from the failure point of view. And what is this surface modification? It is a relatively new term. Actually, it was not there 100 years back. It was there, but it was not there as a organized stream of science and engineering. It is relatively, therefore, a new term that has come up in the last 2 decades to describe the interdisciplinary activities aimed at tailoring the surface properties of engineering materials. Because in engineering materials, the bulk property or the core property and the surface properties, property requirements are different. For example, if you want a reflective surface, the surface should be reflected, not the core of the material. So the surface needs to be imparted with some kind of reflectivity by an engineering or by a technique called surface modification. Now, while surface modification is the philosophy, surface engineering is the name of the discipline. And surface engineering has emerged as a very novel branch of engineering, or an emerging branch of engineering, where even master's program and doctoral programs uh, are being floated in many big institutes. What exactly we do? Through a surface modification process, we actually assemble 2 or more materials by the appropriate method and exploit the qualities of both. The quality of the core material for the strength purpose or load bearing purpose, and quality of the surface for the for combating with the environmental or external or operating environments attacks. Now there are different surface modification technologies like plating. Plating is a very common technique. Electroplating and electroforming are under this plating category. Then you have diffusion processes. Diffusion process in which carburizing, nitriding, um, and all these chromiding, boriding, all these proper processes are there, where actually you treat the surface in such a way that these elements get diffused to the surface, but they do not change the dimension of the component. But in overlay coatings, where you apply coating over another material is deposited on the original substrate, then in that case the dimension does change. Then there are processes like surface hardening and thin film coating, like physical vapor deposition and chemical vapor deposition under the modern surface modification technologies. Today we shall be dealing, or we shall be discussing mostly a coating. What is a coating? Coating is actually a layer of material. It's a different material, a layer of material which is formed naturally or synthetically or deposited artificially, where on the surface of an object made of another material. That means you can have a titanium nitride coating on mild steel. So titanium nitride is altogether a different material. Mild steel is another material which the machine is made up of. And on mild steel component or on mild steel surface, you give a layer of external material, that is titanium nitride, with an aim of either obtaining some technical benefits, or you can also use it for decorative purpose. So there are 2 members in this activity. One is the substrate, another one is the coating. The substrate is the coated object, and coating is the object that is coated. Okay, so there are two different things. One is the base material on which coatings are to be deposited, and coating is the external material that is deposited on the base material. So these are the 2 things. Like in composite we have a matrix and we have a reinforcement. Similarly in coating activities we have a substrate and then we have a external material called the coating, which is deposited on the substrate in order to give, impart, or add some additional property, required properties onto the main base material. So I've already told why the coatings are required. Coatings are required because they solve the component degradation problems. Why the component degrades? Often because of the environmental attacks, because of uh, because of corrosion, because of coming in contact with dust particles, because of coming in contact with saline climate, because of coming in contact with water, etc., or moisture in the air. So there is always component degradation because of this, and the coating solves this degradation problem. and thereby coating also helps in material saving and subsequently enhances the working efficiency of the component. Once the component degradation is decelerated, naturally the efficiency will be enhanced. There are different types of coatings. There are decorative coatings. I mean, there are some products where the aesthetic is of high importance. For example, ornaments. For example, fancy objects. For example, a car. You will say you will buy a car provided it looks nice. If your car is looking like a war tank, you will not buy it. So the outer aesthetics, the outer look must be very good, and for that coatings with the purpose of with a decorative purpose is provided onto these products. That is also a technical, that is also a subject of technical interest. Then protective coatings. Protective coatings are technical coatings which are provided on the surface of any base material whose task is exclusively to protect the object or the main material, base material or the main component from the harmful effect of the environment, mainly the atmosphere and chemicals, as well as from mechanical hazards. Mechanical hazards means if there is wear and friction, if there is high pressure, if there is high temperature in a workplace where the component is put to use, there is possibility that the surface will get degraded because of these external factors, and there you require a protective coating. For example, say suppose you are working, I mean you are using pipes under sea, I mean in the deep sea, then it is coming in contact with the saline water, so very soon the surface will be degraded. So the appropriate coating material must be deposited on these pipes and tubes so that their longevity is enhanced and their performance is bettered. So there can be decorative coatings, there can be protective coatings, and there can also be protective decorative coating. Protective decorative coating means the purpose is not only to protect it from the other mechanical and environmental hazards, but also to give a good look, good appearance, so that its market value is increased. So in the technical coatings, I mean, which is coming under the, or you can say the protective coating is also a technical coating. The technical coatings, that means the coatings provided on a base material with an intention to get some technical benefit are called technical coatings. So you can have coatings that improves the tribological properties. That means it arrests the damages due to the wear and tear and friction. The coatings which enhances electrical properties. Sometimes you can coat a material with a electrically conductive or electrically insulative material so that the surface becomes conductive or insulative accordingly. Then coatings which enhances the solderability, the ability to get soldered. The coatings that protects the material against diffusion. The coating that enhances the some target thermophysical properties. Then coatings which enhances the optical properties. Suppose you want a coating to absorb the light or absorb heat, then in that case you can paint it black, so that black coating is to be provided on the surface. Sometimes you want reflectivity on the material, so in that case you can apply a reflective coating on this so that you can get a benefit out of that. For example, I am telling you, when you are driving on highway, you can see the road markers. So the road markers are reflective materials, so that even if you are driving, you can see the border of the road or the divider from a distance. So there the reflectivity plays a very important role. Even the signboards and the direction boards, all these are provided with reflective coating so that it I mean in the incidence of light, it can reflect and show you the path. There are different coating techniques. There are different surface modification technologies that I listed out, like plating and all, and there are different coating techniques as well, like physical vapor deposition and chemical vapor deposition and thermal spraying. These PVD and CVD are also novel methods, but then problem is that they are very slow processes and they have merits as well as they have their own demerits. And one of the major demerit is that they are very slow process. So most of the industrial applications do go for a technique which is fast, which is less time taking, and which has got more versatility, and that is what is called thermal spraying. So thermal spraying, so today our discussion will be confined on a particular type of thermal spraying technique. Okay, so we must understand what thermal spraying in general is, and then we can go for the specific one, that is the plasma spraying. Now, what is this thermal spraying? Thermal spraying is an umbrella. Okay, it is, there is nothing like a thermal spraying technique. It is actually an I mean that it is actually a what do you say, a category of spraying technique under which there are many processes. So it is a generic category of material processing technique that apply consumables, because you have to apply consumables, because that the consumables are the one which are to be deposited, which are to be spray coated on the base material. So this consumable must be in the form of finely divided molten or semi-molten droplets to produce a coating onto the substrate kept in front of the impinging jet. So this sentence indicates that thermal spraying is for a host of techniques that includes or involves use of consumables or the coating materials, and they are to be melted or semi melted. That means you require a heat source for that, and then you have to have a jet, impinging jet, which will carry these powders to the target surface. Now before we see what actually is thermal spraying, let us let us have a visit to the various applications that use thermal spraying, and you'll be surprised and amazed to see that there is no industry untouched, which is untouched from this use of thermal spray, sprayed products or these coated products. Okay, so the applications are repair or build up worn or damaged surface. Suppose surface is damaged, then you can reclaim it, or you can make the damage up by thermal spray coating technique. You can undercoat for paint, you can do for electrical conductance, you can do this coating for improving the wear resistance, corrosion resistance. You can make this coating for products to make them resistant in high temperature situations, and you can also make them insulative at the surface, as I told before, I mean, in case the working requirement demands it. As I told you, the thermal spraying is not a single technique, it is a common name for a vast gallery of techniques for coating depositions. So in this technique, the coating is produced by a process in which molten or softened particles are applied by impact onto a substrate, and that impact is accomplished by an impinging jet. We must understand at this place what are the fundamentals of this thermal spraying process, how actually it occurs, and what are the various stages. And it is very simple to understand. It's very simple. It is just like if you say, if you want to if you take a uh, if you take in your hand a ball made of mud, and if you throw it to a wall, then what will happen? So if the mud is a wet mud ball, then in that case what will happen? A part of that may stick to the wall, or the whole of it may stick to the wall, or the entire ball may fall onto the ground after hitting the wall, and even after that it will form an impression on the wall. So it will form an impression on the wall that one can make out that something has been thrown to the wall. Similarly, exactly the same way, the thermal spraying technique is carried out. The different steps are as follows. The coating material, I mean, whatever you want to coat, Say, as I gave you the example of mild steel and titanium nitride. Titanium nitride is the coating material, mild steel is the target material or base material on which the titanium nitride coating are to be deposited. So the coating material is molten by the heat source and propelled towards the surface that is being coated, where they impact, flatten, and solidify. In other words, all variant processes of the thermal spray technique generally involve the following features. The features are: the material to be sprayed is heated in a flame or an arc so that it is substantially molten. Because if you want to melt a material, the only way is to apply heat. Now, how you apply heat, from what source you are supplying it may be different, but heat is that which is required for melting or semi-melting the material. This molten material is accelerated in a gas stream, so you require a gas, precisely a high pressure gas stream, which will carry this molten particle in a direction where you are placing the target object, and that should be propelled onto the surface which is to be coated. And these partially fully molten particles flattened, as I was giving you the example of this ball made up of mud hitting the wall. So these partially or fully molten particles flatten upon impacting the substrate and subsequently cool and coalesce to yield the desired coating. You can look at this diagram. So these are the process fundamentals. First, you can have the coating material in the form of a rod or a wire or powder, and that powder will be subjected to supply of certain amount of heat, and that amount of heat must be capable of not only taking it to the melting point, but also should be providing the latent heat of fusion, so that the particles melt and they get into a molten state, and then they come in contact with a high pressure jet, made up of compressed gas, high pressure gas, or stream, and then it will be propelled towards the surface. This is the surface. You can see the hatched line is the surface or the target surface on which coatings are deposited, and the formation of splats are there, and these splats do get formed layer after layer on the substrate surface, and after some time you will see that there is a multi-layer coating formation. You can see the developments precisely in this magnified diagram. The material coming to the molten state, getting accelerated and propelled towards the target surface, hits the surface, forms a splat, and then a number of splats one after another is formed, and so after some time a coating of reasonable thickness is formed by these splats. The same thing, the feedstock powder particle melting, molten particle acceleration, then particle impact, and then finally you have the full coating body deposited on the material body, base material. These are schematics. So today I'll be showing you a lot of photographs which will give you an insight and idea about the coating formation. So here also you can see the thermally sprayed particle impinging onto a splat surface like this. You can see in this diagram there are unmelted particles, there are voids between different particles, there are oxide inclusion because it is coming with the atmospheric air. There might be formation of oxides in between, and then the splat formation, and you can see the spraying direction and the spherical particle after being impacted, what kind of splat it forms. And we know why I'm telling spherical particles, because you know that when anything is melted, when it becomes a liquid, then it will take the spherical shape due to a physical property called surface tension. All of us know it from physics. And then, as I told you, the melting of these consumables or the coating materials may be accomplished in a number of ways. The consumables can be introduced into the heat source either in a wire form or in a rod form or in a powder form. And what can be sprayed? These consumables can be metallic materials, ceramic materials, or even polymeric substances. So any material can be sprayed as long as it can be melted by the heat source employed and does not undergo degradation during heating. So it should not undergo a a large scale degradation during heating, and it can be melted with the absorption of heat, then it can be sprayed. So as I told you, the versatility, look at the versatility of the process. It can be metallic material, it can be ceramic material, and it can be polymeric substances. Today we will be discussing mostly about the ceramic coating formation. And there are two basic ways of generating heat. How you generate heat? Okay, heat source is required, agreed, but where from the heat comes? And depending on where from the heat comes, you have different types of thermal spray techniques. Like today we'll discuss plasma spray technique. It is because the heat source is plasma. Plasma provides the required heat for melting of the material. That's why it's called plasma spraying. Otherwise, it is a thermal spraying technique. If it is coming from an arc, it is arc spraying. If it's coming from a flame, it is flame spraying, like that. So the heat source can be obtained by combustion of a fuel gas or by a high energy electric arc. We are coming to the process, but as I assured you few slides back, that we must have a look at the use of possible use or applications of thermal spray coatings, and you can see the list of industries that employ thermal spray coatings. And look at this and a host of industries, and you will find there is no industry untouched. Even if you name some other industry other than this, that also will be using thermal spray coating. So you have aerospace, construction industries, electronics industries, defense, automotive, biomedical sectors, dredging and food processing, marine and mining, petrochemicals, steel plants, textile and power plants, pulp and paper, oil and gas units. So everywhere you will find rampant use of thermal spray coatings. So thermal spray coating is no more a you can say the technique may be a novel technique, but it is not a novel material as such, because the conventional thermal spray coating materials are being used everywhere universally. What is novel about thermal spray technique is that you have to explore of the new materials. What can be coated, then that will give some novelty to your work. Now look at the aerospace industries, and there you use coating components, coated components, because of their strong corrosion resistance, high temperature resistance, and you normally use thick coatings. They require it has to have sufficient coating adhesion. I'll tell what coating adhesion is, then abrasion resistance, etc. And you can see on the right hand side, right bottom, you can say these are the specific parts. So instead of just telling that it is used in aerospace industries, we can also list the components, specific components. I mean, pinpoint the applications of these thermal spray coatings in the aerospace industries. So look at the turbine blades, the piping system, okay, and the journals, the bearings, and they are all thermal spray coatings are being used. This is how a coating process is accomplished. I will, if possible, I will show a video where you will get an idea about how the coating does take place. And this is also part of an aerospace turbine unit, the opened one. So here also the blades are coated with thermal spray coating. In the automotive industries, there are many parts: exhaust pipes, turbochargers, piston rods, brake disc, axle, shift forks, silencers, crankshaft, hydraulic rams. Everywhere thermal spray coatings are being used. So the list is very long, and just see the photographs, the different parts of a automotive, how they are coated, and these are pictures picked up from industries where different parts like the cylinders and the silencer system, the exhaust system, all these things are being coated both internally and externally. These are the different parts, the coated parts or finished products. Of course, the coating material that is coated on these substrates or components will be different depending on the demand of the application. Coming to biomedical industry, these coatings do have a lot of applications, particularly in artificial limbs and this bone and hip joint replacements. So you can pin. But here the additional requirement, apart from strength and durability, the additional and most important required property is the biocompatibility, because it is to be planted inside human body. So it has to be it is to be compatible with the other parts of the body, the blood and the flesh and nerve system. So the biocompatibility needs to be checked. Civil and construction industries, no need to mention the applications. Anywhere and everywhere you see, you will find thermal spray coated samples. Power plant industries, starting from turbines, cyclones, boiler tubes, shafts, rotors, turbine rods, pumps, everywhere you will get a signature of this thermal spray coating. Now this is a steam turbine. You can see the blades are coated with thermal spray coating. Of course, the coating material here is very expensive and very delicate. So the process is to be accomplished very, very precisely. So these are also some pictures picked up from the industries. So this shows the thermal spray process technique. Now, as I told, the power plant where you have this rotor system, turbine system, there the use of thermal spray coatings are uh, very large. These are the different parts, finished products after being coated, and you can see the coated surface, and you can see that these surfaces possess properties that are different from the properties of the material that they are made up of. That's the different, and that's the beauty of surface engineering. The coated material or the coated surface will exhibit fairly different properties compared to the properties, intrinsic properties of the base material. And these properties of the outer surface are the required properties for the component, because it is the surface which will be coming in contact with the direct environment, the immediate environment. So we saw a gallery of thermal spray applications. Let us discuss what are the benefits of this thermal spray. Benefits that this coating can be adapted to specific criteria. Comprehensive choice of coating materials can be made. Coatings can be post-treated after being coated. Thick coatings can be applied at high deposition rates. Parts can be rebuilt quickly and at low cost, usually at a fraction of the price of the replacement. That means if you are going to reclaim a part and make up for the damage of the part due to wear and tear with using thermal spring, then that will be a costly activity, no doubt, but that cost will be still less than the cost of replacement. So components with a coating will have longer lifetime, it is obvious. Their durability and the lifespan will be more. Thermal spray coatings may be applied both manually and automatically. That is an element of versatility that is associated with thermal spray coatings. Then there is no dimensional limits to component size. So that means the component of any size and in fact any shape can be coated. Wherever the gun can go and see, that part can be coated. It is environment friendly. It is incompatible with the substrate material with a higher melting point than the substrate. That means it's a demerit. If the substrate has lower melting point, then there will be problem, and no cure time is needed, unlike many conventional paints. And it may last longer than the conventional paint, which can result in a lower life cycle cost. Suitable replacement for hard chromium electroplating. So once you have identified a coating material which is cheaper than chromium, then this activity will be less costly than to have a replacement for hard chromium electroplating. So these are good things about thermal spray technique. There are limitations though, but this thermal spray process, as I told you, till now we have not gone to plasma. We are only discussing thermal spray in general. So as I told you, the heat source can be made up from an arc or can be made up from combustion. Today we will discuss the arc process, in which we are getting the heat from generation of a plasma arc. So if you see the schematic of a thermal spray process, then there are different stages, and different variables are there, and all these variables do play a great role in deciding the quality of the coating, and the temperature, the particle size, the degree of melting, the thickness of the coating, and all these things, they will decide how good it will perform in the actual workplace. uh, I think in the next session, Dr. Mantri will highlight more on this, because he'll be talking about thermal barrier coatings. So there, he will, I think he will cover all these things as well. So let us come down to plasma spraying. What is plasma spraying? Plasma spraying is a thermal spraying technique which uses plasma as the source for heat in order to melt the coating material. Otherwise, rest of the process fundamentals, everything is same for thermal spraying, because after all, it is a thermal spraying technique. Now, what is plasma? Plasma, as we know, is the fourth state of matter, and is distinct from solid, liquid, and gaseous state. When you heat a solid, you get liquid. When you heat a liquid, you get gaseous state. Similarly, when you heat a gas, then what happens? The gas will get dissociated to, or ionized to, dissociate from molecule to atoms, and get ionized from atoms to ions, and then you get a cloud of positive and negatively charged particles, the ions, the molecules, and the atoms. And that cloud, which is quasi-neutral in nature, although it contains charged species, but as a whole it is quasi-neutral, and that cloud is called plasma. And it is an electrically conducting medium, and at the same time, though it is an ionized state of gas, it is not called or categorized as the gaseous state, because plasma does not follow the gas law. Conventional gas law, the Charles law, Boyle's law, universal law, etc., are not followed by plasma. Plasma behaves differently, and it is considered as not as a gas, but as a state beyond the gaseous state, that is the fourth state of matter. This is what I was telling. Solid to liquid, liquid to gas, and then further application of it will give rise to the generation of plasma. And it is the fourth state of matter. Plasma we can see in the lightning on the sun's surface, and within a electric bulb, the plasma cloud can be visualized. This plasma spraying is one thermal spraying technique, one typical and very widely used thermal spraying technique that utilizes the exotic properties of the plasma medium. Plasma medium has got its own beautiful properties, and very conducive for industrial applications, and that is explored, that is utilized to develop coatings on a variety of substrates of complicated shape and size, and it can use also a wide range of materials ranging from metallic to polymeric ones. So I repeat that plasma spraying is the most versatile thermal spraying process. I have already told before. And what happens here is that an arc is created between the tungsten tipped copper cathode and an annular copper anode, and both are water cooled, and this plasma generating gas is forced to pass through the annular space between the electrodes. While passing through this arc, the gas undergoes ionization. Because of the high heat, high temperature, it gets ionized, and that results formation of plasma. So you can see that this is the cathode anode combination. This is where the argon, which is the gas which is to be ionized along with hydrogen, is passed through, and the water is circulated for cooling purpose, and water is circulated and coming out here, and the plasma is formed. The powder is fed from an external arrangement. So it is externally fed powder, and this is the powder which is to be coated. So you can see this suppose this is silicon oxide. You can see the silicon oxide particles, and it in the film state, it is the spray film. Okay, and this powder is fed externally, and this powder, when it comes in contact with the plasma, resides within the plasma jet for some time, and during that duration, it gets melted, and the molten particle in the form of droplets gets accelerated like this, get accelerated towards the substrate, and this is the splat that I was talking about. When it hits the surface, it forms a splat. So one particle will form one splat, and the particles are continuously hitting the target. So therefore, there will be continuous deposition of continuous formation of splats, and all these splats layer by layer together will form the coating body ultimately. So this is again the description of the same thing that I have spelled out, and the different steps. And the here I would like to tell that the um, maximum temperature that can be achieved is very large. It is beyond 10,000 K, and sometimes for some gases it also reaches 20,000 K at very high level of touch input power. That means when the current and voltage combination is made high, then the power input to the plasma touch becomes even higher, and then you can reach a temperature as high as even 20,000 K. And the beauty is that at this temperature, any material can be melted. Any material can be melted, and that is the advantage of plasma spray process. So, if you list the plasma spray process, the advantages, then any powder which melts without sublimation. Okay, the condition is that it must be melting, but at the same time should not sublimate. Sublimation is the process of going directly to the vapor phase, bypassing the liquid phase. So that should not happen. It should only melt. So powder which melts without sublimation can be coated. The substrate temperature, although the flame temperature is as high as 10,000 K, but the substrate temperature will not increase because the flame does not come in physical contact with the substrate. So it remains at a distance called the TBD, touch to base distance, and the substrate temperature can at best go little beyond the atmospheric temperature, that up to 50 degrees centigrade it can go, because the environment gets heated up totally. There is no restriction on the size and shape of the job. That's the versatility of this process. And the coating process is fast. That's a very unique advantage or merit of this plasma spray coating process, because coating process is very fast. In seconds or in minutes you can finish coating of even 1 square meter of a component, and the thickness can go from few tens of microns to millimeters. That means this technique is suitable for thick coatings. In the coating world, any coating which has got thickness over say 50 micron or 100 micron are called thick coatings, and below 10 micron are called thin coatings. So for thick coatings, this process is applicable. This process is not applicable for thin coating requirement. You can see that complicated shapes and intricate shape and size of components can also be put to use for plasma spraying activity. So that is the versatility of this process. Even if like a curved shape like this one, or internal shapes like inside of a hollow tube, all these things can be done with plasma spray. This is a typical plasma spray setup where you have um, the different units like powder feeder, the um, control console, and the plasma gun, then the cathode anode combination, the water cooling system, and gas cylinders from which gas is supplied, plasmagen gas is supplied. All these things you can have. This is a picture of a plasma spray coating facility which was there at NIT Rourkela. Right now it is not there, and we are looking for a more advanced and automated system now. This is the schematic of the same setup, where you have the gas cylinders, the control console, the electrical power system, then you have the um, plasma torch, then you have external powder feeder from which the powder is fed to the flame. So the schematic is this. Schematic diagram of a complete atmospheric plasma spray setup is this. Why I am telling it atmospheric plasma? Because this activity takes place under atmospheric conditions, not in a controlled condition. If it is in a conducted in a controlled condition, then we say it is restricted plasma. So I had little experience of getting involved in plasma research. So this is the lab, that is Laser and Plasma Technology Division lab at Bhabha Atomic Research Center, where I was. I carried out a major part of my doctoral research, and this is the place. This is the lab which is housing the laser and plasma technology division, where you have the plasma spraying facility, particularly the atmospheric plasma spray facility. You also have LPPS, that is a low pressure plasma spraying facility, but the science of low pressure plasma spray activity is altogether different, so I am not discussing it now. Then this is a old picture of mine at BARC, where the plasma spray coating was done by me manually. Now there are automated systems where you can control it from outside the chamber, and automatically it will do. But here manually you can control the number of passes, you can control the thickness, and also you can vary the spray distances at your end. This picture I have already shown you, and this is some of our students. They did coating. Even Dr. Mantri, who will be speaking in the next session, has also prepared his coated samples here at NIT Rourkela in this facility long back in 2004 or 5. And so that was working well, although it is an indigenous setup and a manual system. It is a manual setup, and it is less expensive. But then the control in a manual system is always like depends very much on the skill of uh, the person who is coating it. So it is a skill based technique, you can say, if you are doing it manually. If it is an automated system, you can program the whole thing. You can program the number of passes, you can program the powder feed rate, you can program the temperature, and then accordingly it will operate. Now coming to the conventional coating materials. What are the materials that are normally conventionally coated? The conventional materials are carbides, oxides, uh, carbides like tungsten carbide, titanium carbide, then silicon carbide, zirconium carbide, etc. Oxides like alumina, chromia, titania, zirconia. Metallic like intermetallics, nickel, chromium alloy, trivalent, or diamond coating. These are the conventional materials. But these are the different stages of plasma spray process. This slide should have been before. And once you conduct a plasma spray activity with this conventional material, then normally you have to go for characterization of the coating. And the coating characterization involves evaluation of certain essential properties like coating adhesion strength. That means with what adhesive force, or with what force it adheres to the substrate. What is the degree of what is the intensity of mechanical interlocking between the coating material and the substrate. That is I mean, an idea about that is obtained from the evaluation of coating adhesion strength. Then porosity, measurement of porosity is also important, and it is done with a image analysis technique, and that gives you an idea about what is the fraction of volume, what is the void fraction of volume that lies within the splats, okay, and which is detrimental to the strength of the composite. It's not desirable in many applications, but the measurement of that void fraction is essential, because that only will tell you what is the quality of the coating, what kind of coating it is. It's a good coating or a bad coating. Then deposition efficiency is a measure of the coatability of the powder. The powder that you are using, how much coatable it is. All powders are not coatable. If you want to, if you just bring anything arbitrarily XYZ, it cannot be coated, because the coating material should have certain characteristics, and how much coatable it can be depend on its own specificity, its own latent heat of fusion, its own melting point, its size, its shape, its composition, all these things. And once a coating is formed, it is very essential that the micro hardness of the coating is also evaluated or measured, because coating in many cases is a heterogeneous structure body, and the hardness at different places and optically distinguishable phases must be evaluated so that you get a mean micro hardness value, and that is essential for wear related applications, particularly tribological applications. Then of course you can go for additional characterization like coating morphology, that will give you an insight to the various features in the microstructural level, the thermal conductivity and wear resistance. If you're using it for a wear resistant purpose, tribological purpose, you must have to go for the wear properties. I've told this already. Yes. Because gradually we are coming to industrial waste, so I'm telling you that the in a coating activity there are different components of cost expenses. Okay, but the major component is the cost of the powder. So in a coating activity, 50 to 56% cost goes to the cost of the powder. That's why the coating becomes an expensive activity. Now if you want to make it cheaper, or if you want to make it less expensive and affordable by everyone, then you have to you have to focus on that component which is costing more, that is the powder. So now the spray gate powders or the conventional powders which I had earlier listed out are expensive powders, and in place of them, if one can think of low grade minerals or industry wastes or construction waste which can have coating potential, then drastically the cost of the coating activity will decrease. With this in mind, actually we started with our research with some industrial wastes, and we got very promising results, and that research is still going on, and we are exploring new and new uh, industrial waste. Recently we are successful in developing the marble dust coating on metallic substrates using not using plasma spray. We are using another technique called high velocity oxyfuel, and uh, my students are involved there, and uh, with the technical direction from guidance from Dr. Sisir Mantri, we are carrying out that coating operation, and we have been successful to a large extent. And over the last few years we have developed these coatings. Look at the list: red mud fly ash, red mud aluminum, red mud carbon, fly ash aluminum, alumina titanium, fly ash ilmenite. So if you look at this combination, these are development of composite coatings, means coatings of two materials together, mixed together, that mixture is coated. So if you look at this mixture of materials, combination of materials, you'll find that except the alumina titania, rest all combination, the other combinations do contain some industrial waste. One or either both of them are industrial waste, or at least one of them are industrial waste. So these coatings have already been developed by our group, and I will share my experience with at least one or two such coatings. First one is red mud fly ash coating. So red mud, as you know, is a waste that is generated in the alumina plants, where alumina is extracted from produced from bauxite and through Bayer's process. And in Odisha, you know, the a big company is there, Nalco, and they have a plant, alumina plant at Damanjodi. So we collected some red mud from the Damanjodi. You can see the picture here, and this is looking red because of its high content of iron oxide, and this is a huge waste, and the disposal of this waste is a big problem for the alumina industries throughout the globe. Although Bayer's process is 150 years old, still the disposal and utilization of red mud is remaining a challenge to the engineers and the scientific community throughout the globe. Either this red mud is dumped into the sea, provided sea is nearby, or it is simply dumped into the open space. When it is dumped into the open space, then being carcinogenic, it creates health hazards in the immediate vicinity. The habitants who are staying nearby are affected. Uh, their health is getting affected, and it is a known pollutant. But if it can be used for some value-added applications like composite making or like coating making, then maybe a part of that can be properly utilized in order to make some value-added product. In keeping this in mind, we tried this red mud coating, and we went for a X-ray diffraction test of the red mud. We found different constituents like silica, iron oxide, calcium carbonate, little bit of aluminum oxide as well. And then we uh, put it into, I mean, we sieved it into a to get particle size in a range of say 80 to 100 micron, around that range. And we went for a chemical analysis that suggests that it contains lot of iron oxide, aluminum oxide, sodium oxide, calcium oxide, and titanium, silicon oxide also. And its density is 3.3 gram per cc. And thinking that the constituents of this red mud, the silicon oxide, the aluminum oxide, iron oxide, because individually they are all good coating material and tested coating materials. So we thought that why not the mixture of this material will be used as a coating materials, and we tried and we succeeded. And we not only succeeded with red mud coating alone, we also mixed red mud and fly ash in definite proportions. And fly ash, as you know, is another industrial waste, and it is needless to mention that fly ash is generated in power plants and causes a lot of health hazards. Of course, fly ash is being used for brick making and pit filling, but in spite of that, in the power plant areas, you will find tons of fly ash getting accumulated in open fields. So for that, fly ash is also mixed with red mud in different proportions, and the coating was done. So you can see that we tried with red mud 100%, red mud and fly ash in 9:1 ratio, red mud and fly ash in 7:3, 5:5 ratio. Then we mixed a little bit of carbon powder with red mud, uh, because carbon is a reducing as agent. And then red mud is also mixed with 5% of spray grade aluminum, just to see how it affects the different coating properties and coating quality. And we tried with different substrates, because the coatability of a particular coating material cannot be same on uh, all the metals or all the surfaces. So you, because the mechanical anchoring depends on the substrate nature of the substrate as well as nature of the coating material. So in order to see that variation, we tried with aluminum, copper, mild steel, and stainless steel surfaces, and then we coated this using a plasma spraying technique. After these coatings are formed, then the characterization was done. The essential characterization that were carried out are coating adhesion strength, the porosity, measurement of the porosity and void fraction, the deposition efficiency, micro hardness, and of course the coating morphology was also observed under scanning electron microscope. This is a setup. This is this is a very familiar machine, universal testing machine, UTM, and using this UTM and with this um, the holder which was designed by us, we tried to evaluate the adhesion interface bond strength or the adhesion strength following the ASTM standard of 633C, and this is the variation of coating adhesion strength. Then we found that as we increase the torch input power, the coating adhesion strength, the coating adhesion strength is of paramount importance for any coating characterization, because it tells you how, what should be the force that you must apply to peel it off the substrate. उसको निकालने के लिए कितना force चाहिए, that is measured, the adhesion strength is a measure of that. So we saw that as the torch input power is increased, so they are monotonically increasing, but after reaching a maxima, there is a drooping of the curve. So that occurs due to various reasons, like at high temperature the particles fly off, some particles they get vaporized, all these things. Then erosion resistance. Erosion is a particular wear mode which occurs in dusty environment and causes lot of degradation to the component. So our purpose was to make erosion resistant coatings. Therefore, these coatings are subjected to erosion test, and we found that the red mud coatings are fairly they have fairly good erosion resistance and can be used for erosion resistance purpose. The deposition efficiency was not very high, but then in the plasma spray world, 25 to 30% is considered good. We got a maximum of around 27-28% of deposition efficiency, and it says that out of the powder that you are feeding, what fraction of that is getting deposited on the substrate. That is deposition efficiency, and this is very relevant and very important from economical point of view for spray grade expensive powders. But then even if it is very low here in this case of red mud and fly ash composite coatings, but still, but it is not very important for us because these materials are available free of cost. They are quite cheaper compared to the spray grade conventional powders. This is a comparative picture showing the coating erosion resistance, erosion rates with conventional material and our material. So with good erosion resistance, these coatings can be used for agricultural implements, because agricultural implements do encounter slurry erosion during at their workplaces. Then you can use them for coating the conveyor belt rollers, which are continuously encountering friction with the belt and the material that are loaded on the belts. You can it can be used for the coal bands used in power plants and furnaces where the pulverized coal is supplied to the furnace. Those pipes, they get eroded from inside because of the impact of that high velocity pulverized coal particles. So those bends and the inner surface of the pipes can be coated with this red mud. The exhaust fan blades can also be coated if they are subjected to erosion, particularly when they are used in deserts or in dusty mine sites or mining sites. So I told you about red mud, but there are many other industrial wastes, and in India we have no dearth of industrial waste. We see waste everywhere and anywhere. So many of these industry wastes and construction wastes can be investigated upon, can be explored, can be tried for coating purpose. Plasma spraying is just one route. There can be other routes like flame spraying. There can be other routes like high velocity oxyfuel spraying. There can be other routes like detonation spraying. So there are many ways where these powders can be tried for making them usable, making them good candidates for coating purpose. And they are, the list is long, but I am listed a few: red mud, copper slag, cement bypass dust, fly ash, LD sludge, blast furnace slag, granite dust. Out of this, we have tried with red mud, copper slag, and fly ash, LD sludge, LD slag also we have done, and right now we are doing with marble dust. So before I conclude, I would like to show you a I like to show you a video that gives an illustration of how plasma spraying technique is used, is accomplished, and this is automated plasma spray technique which is existing in IMMT Bhubaneswar, and this picture was taken there, and this picture was taken, and the credit goes to Dr. Sisir Mantri, who was having this machine. Just tell me, can you see the video?
Yes, sir.
Yes.
Oh, sir.
This is showing the generation of plasma at the nozzle tip, and this is a target surface. So that was about that was just a video clipping of plasma spray coating process, and with that, I'm coming to the concluding part of this session, uh, and I want to impress upon the young researchers, if any present here in this audience, those who are thinking of working in this type of area and looking for topics but not getting uh, an appropriate topic or appropriate material to work with, they can think of in this line, that this coating science is still an open-ended research area in which there is a wide scope of doing work. Although you will find thousands and thousands of papers, but still there is wide scope of doing new work, and that can be done by exploring new waste materials that can have coating potential, and they can be investigated upon, and new application areas can be thought of. And For your information, this is a book authored by me and my guide, Professor S.C. Mishra, on novel coating materials, which describes the plasma spray coatings of red mud, plasma spray coatings in general, and red mud coatings in particular. So this is published by Lambert Academy Publishers, Germany. And with this, I thank you all, and particularly I thank the organizers to have given me this opportunity to speak on a subject which is very close to my heart, that is plasma spray coating. And thank you, with a request that this is my YouTube channel, Alok Sir Speaks. For technical and for videos of technical and some non-technical contents, you can watch, share, and subscribe this channel, um, and watch some of my talks on coatings and composites through this channel. So with this, I think I will wind up, and with thanks to the organizers once again.
Thank you so much, sir, for the excellent lecture.
I think I finished in time.
Sir, before time.
Okay.
So thank you for sharing your experiences in your research area with us. We are so much grateful, sir.
Thank
We
you.
will have a break for 5 minutes, and then we'll start our next session. Our second expert guest of today is Dr. Shishir Mantri, Principal Scientist, CSIR IMMT Bhubaneswar. Thank you, sir.
Okay.
Sir, I do have